Good afternoon, everyone. I am Animesh Jana. So at present, I am working as an R&D head for temperature calibrator and furnace. Today, we are going to discuss about different uncertainty components and little bit about uncertainty calculation for the temperature sensor and also the dry block. So, but before going to that part, let me a little bit introduce ourselves. So, we are Tempsens instrument, and we have a 60% of revenue comes from the different type of temperature sensor like RTDs, thermocouples, and 29% revenue dedicated for the different type of compensating cable or MI cables, and another 11% for the heaters, temperature calibrator, or we also provide the different type of heating solution for industrial application. We have a 4 unit. We are based in Udaipur. One unit dedicated for the temperature sensor, like for RTD, thermocouples, and another unit dedicated for the different type of heaters, pyrometer, thermal camera. And unit 4 is dedicated for the industrial and laboratory furnaces as well as the compensating and MI plants. And also we have 2 units outside India. There is one is from Germany, Tempsen, Germany, and one is in PT Tempsen Asia Jaya, that is in Indonesia. So we have all necessary certificate for the industrial application, whether for our all the product, either for the temperature calibrator, furnaces, MI cables, heaters. So we have necessary certificate to explore ourselves in the all the sector, industrial sector. We have very strong marketing team. We have our all the region in India, north, east, west, south. You will get our presence, and also in the world, in Asia, Saudi Arabia, Japan, or America, we have our Tempsen branch where we also manufacture, and as well as our sales representative is there for give you all type of support for the instrument purchasing, selling, or after servicing. So let us discuss about the uncertainty components of a dry block temperature calibrator. As you know, uncertainty is very major components, and in any labs or for any temperature sensor, you need to calculate the uncertainty. Now, what is the uncertainty? If you go for the definition, it is saying that it is the expression of statistical dispersion of the values attributed to a measurement quantity. So in general term, if I say it is nothing but the doubt in the measurement system. If we take any measurement, we have a doubt in it, and the depth of the doubt defines that how much we are believing in our measurement, whether how much it is good or bad. So that is nothing but an uncertainty. Now we will discuss the uncertainty components for the dry block temperature calibrator. So I will discuss about all the major components that contribute to the uncertainty in the dry block temperature measurement. So before going to in that part, let me discuss about dry block temperature calibrator. Now dry block temperature calibrator is nothing but it is a insert or block, and where different we make the drill based on your sensor diameter, and we have to heat that insert in that metal block, whatever the set point we have to reach, and we put our master sensor and the test sensor, we make the comparison. Like it is the diagram of a dry block temperature calibrator. It is nothing but a heating zone where we wrap the heater, or you can put the heater zone mainly, and we have the controlling sensor that directly connected to your controller, and the metal insert we put inside, and metal insert have a different type of holes, and where you can put your master sensor and test sensor. So basically it is nothing but a comparison type temperature calibrator, where based on the master temperature which is calibrated in a lab, and you put your test sensor, and comparison method you check whether your test sensor have any drift or any test you have calibrated your test sensor. So in that, basically we dry block use where it offer the lightweight and compact design. Normally it is very portable. So it is best used when you are for on-site calibration or field application, even in lab application. We use dry block temperature calibrator. And another advantage is that it is normally fast heating and cooling is there. and we don't use any oil inside it. So basically dry block have a air in medium. So sometimes it is clean and safe. For like for liquid temperature calibrator, we use different type of liquid, either methanol or ethanol, or different type of silicone oil, alcohol based liquid for reach the different type of temperature for -40 or -80. But in dry block we don't use such liquid, either for Peltier based or thermoelectric cooler based, or it is FPSC based, or it is heater based. So basically dry block we don't use any oil in it. So that is why its name is dry block temperature calibrator. So before going to calibrating our dry block temperature calibrator, the some important factor I would like to discuss. Another first point is the it should have sufficient thermal volume. Is that the sensor we are putting in the insert, so that insert volume must be much larger than compared to the sensor volume. If it is not there, so definitely there will be losses will be there, and you will get the wrong reading. There will be the insert, that mass should be much more higher than the insert to give you the correct reading and get the correct uniform result. And second should be the your proper immersion depth. Sometimes this happens during your comparison calibration. If you put master sensor and test sensor in different depth, then definitely there will be big error you will get. Or if your normally controlling sensor is bottom side of the insert or bottom side of the furnace, so if your master sensor or test sensor is not properly immersed in the up to bottom, so it will give you the very large errors. So you should confirm that your master sensor and test sensor should be immersed minimum that specific depth, like for the its immersion depth at length to get the proper and accurate. We do we have to, in dry block temperature calibrator, we have to drill the specific diameter for suit the different diameter of the sensor. Normally, if you have a sensor diameter of 6, so then we make the holes of the 6.5 mm. So it gives clearance about 0.25 mm. So for any sensor diameter, we standard we take the hole diameter 0.5 mm higher than the sensor sizes. So in we Tempsens offer the variety of insert for dry block temperature calibrator. So first, second one is the external reference sensor. So let us discuss some points about internal reference sensor. As I just some slide before, I explained you that it is the controlling sensor, but sometimes it is also considered as an internal reference sensor. You normally have two ways you can check the temperature of the dry block. One is the internal reference sensor, and this sensor is pre-drilled in the heating zone of the temperature calibrator. And another is the external reference sensor, where you have to put the extra master sensor or your additional sensor in the insert section. You have to give it from the externally. So it is the external reference sensor. So for these two reference sensor, you can check the actual temperature of the dry block. Now let's say for if you are using internal reference sensor, you can see it is normally for any manufacturer, this sensor has been fixed in the bottom side of the heating zone. So what happen if you are using external sensor, or for calibration purpose you are going to put your test or master sensor, if it is if it is touch the bottom and your internal reference sensor and the master sensor at the same line, then it will give you the very good reading. And sometimes customer also prefer this internal reference sensor, because in that condition you don't need to take the additional carry, you have to carry your extra reference sensor. So for portability, sometimes customer refer for the internal reference sensors. But what happen if sometime if your sensor is short length or don't able to go inside, sometimes sensor come with thermals or other flange connection. So in that condition, if you consider the internal reference sensor, then it will give the big errors. So the internal reference has some definitely has some advantages, but if your sensor is not able to be proper immersed in the dry block, then definitely it will give you the big errors. So for the internal reference sensor, we have to make sure that internal reference immersion depth should be sufficient and it should touch the bottom at least. And the second one is the external reference sensor. As I told you that external reference sensor nothing but the sensor what we are putting from the outside for maybe that master or standard sensor that had been calibrated from different lab or you have tested it and you have certificate for that. So you have to put it from outside, and from that external reference sensor also you can check the reading of the dry block temperature calibrator. Now, the advantage of the external sensor calibration smaller the sanitary RTD or some small length RTD is there. So for calibrating for that, if you immerse the same length of the master, so it will give very that condition for the small sensor that rectify that uncertainty and give you the very good result in that condition. So definitely external sensor relatively give you the better uncertainty with respect to your internal reference sensors. And third one is the axial temperature homogeneity. There is a big uncertainty component for a dry block temperature calibrator. Normally what's happened that axial temperature refers to the temperature difference when we check the temperature from vertically. Let's say when your temperature is at bottom, if you're pulling upwards slowly, so then you can see that temperature is decreasing. So it is nothing but your axial temperature is very bad. Normally as per Euromet standard or what standard we following, normally 40 to 60 should be there, that from the bottom it should be homogeneous, means that temperature should not be changed in the temperature region. So basically 40 to 60 from bottom side, it should be homogeneous for the axial temperature. So here we are just discussing that if your axial temperature is homogeneity is bad for any temperature calibrator, then it will give you the significant error for the short or short length temperature sensors. Like if sometimes you are using thermocouples as a master or RTD master, or on the other side, if you are using master as a RTD and test as a thermocouples, or master as a thermocouple and test as a RTD, if your axial temperature homogeneity is not there, you will get definitely a bad result. So at least for any temperature calibrator, you should have a 40 to 60 homogeneous region from the bottom. So this is the diagram on metrology temperature calibrator, which is the multi-zone temperature calibrator, specifically designed that when you are, even if your sensor pulling upwards, so you must confirm that up to 60 you get approximate 0.4 or 0.5 not more than that. So as I say that axial temperature homogeneity is very important for the short length of temperature sensor you are going to calibrate, or different type of master you are using than your test sensor. And fourth one is the radial uniformity or the temperature difference between the boring. So what happened, as I say that in the insert for the dry block temperature calibrator, we make the different type of holes in it. So ideally there should not be any difference for if I put the sensor here or after some time here, there should not be any difference after stability, but actually it's not happening in practical cases. Sometimes what happen, there are many certain parameters there, like we are wrapping the heater outside of the insert or heating block, or sometimes we use the Peltier cell. So all it has adds its own limitation, and sometimes it's not give the perfect contact resistance to everywhere. So that is the one of the more general problem where it give you non-uniformity radially. So or sometimes customer use wrong boring, like if, as I say, if we give the 6 diameter, they have a sensor. Sometimes they use 8.5, 10.5, or 12.5 diameter hole they are using. So that time you will get the very bad radial non-uniformity you will get. So this is the reason sometimes you get the hole to hole difference in the insert section you will get. Also, if your if the insert touching the hole more one sided and less in the another sided, or sometimes you put more sensor in one sided and less sensor in the another side, then also you will get the radial non-uniformity for dry block temperature calibrator. And fifth one is the loading effect or influence of loading. So what happens when your furnace is a certain temperature, let's say it is the very high temperature 600 degree or 650 degree centigrade, then the top side of this furnace will leak the temperature. It loses the temperature at the environment, because the environment temperature and the your dry block temperature is a much in a different state. So the losses will increase as per the your rising the temperature of the dry block. So what happens if your number of sensor is more, or the thick you are using the thick sensors, then the losses will be more. So this is the significant error you will get for the dry block temperature calibrator. You are using many sensor at a time, or very thick sensor at a time, then will get very big margin of errors. We call it a loading effect for your reading you will get. And sixth one is the stability over time. For every dry block temperature calibrator, stability is one of the major components also. Means you have to give proper time to reach to stable your master sensor, test sensor, and the furnace as well before get any reading. Stability is nothing but when your system temperature of the furnace or calibrator should be stable over a longer period of time. As a standard, we consider the 30 minutes of time. Means in 30 over a 30 minutes of time, your temperature should be stable, and if not stable, what is the fluctuation? So we calculate what is the maximum and what is the minimum, and based on that we calculate the stability of this temperature calibrator. So why it is an important? Sometimes, as I say, there is different type of sensor like RTD, thermocouples. So there is a different type of sensor is there. So all don't have the same speed of response. So let's say you set the temperature in a temperature calibrator 150 degree. So controlling sensor, that is the internal reference sensor, is very near to your heating zone. So it will very fast it will go to the your set temperature. But the master temperature or the test temperature will be take relatively larger time, because it is in a different zone or different insert. So what happens if in a graph, if you see that set temperature within 5 minutes, let's say it reaches 150. Sensor 1 within 7 or 8 minutes, it reaches that set point. But sensor 2, it take more than 17 or 18 minutes to reach the stable temperature. Now, if you take the temperature in between 10 minutes or 12 minutes, you will definitely check, you will get the big margin of error with the comparison of your master temperature. So that you have to give sufficient time for the calibrator also, as well as for your master and test sensor to take any, you have to comment any uncertainty for a particular your test probe. So I'm giving an uncertainty budget or example for a dry block temperature calibrator. Let's say you have a temperature calibrator operating at a 400 degree centigrade, and these are some parameters which contribute the uncertainty. Let's say it is a standard thermometer uncertainty for your reference sensor. Another one is the resolution of the controlling thermometer, and hysteresis also is there. There is another uncertainty components for the dry block temperature calibrator. It means when you are increasing your furnace temperature, or you get the temperature, let's say you are at ambient at 100 degree temperature, you take the master reading. Now you are go to the maximum temperature and again decreasing to the 100 degrees. So definitely you will not the same reading when it is increasing or decreasing. So that hysteresis there will be there for any dry block temperature calibrator, and it is also a uncertainty component for dry block temperature calibrator. Another is the radial and the axial inhomogeneity in the temperature block, and the another is the steam losses or the loading effect for the dry block temperature calibrator. And another was the stability, yeah, temperature variation during the time measurement. Normally we consider is the 30 minutes. So let's say for the reference thermometer, everything you consider, you have a certificate for that, and it is you already get it in certificate form. It is 0.03 degrees centigrade with a confidence level 95% or K equal to 2 factors. and have a hysteresis of plus minus 0.05 degrees centigrade, and resolution have a 0.1. So the resolution limit would be plus minus 0.05 degrees centigrade. And the inhomogeneity, let's say for the axial homogeneity and the radial homogeneity combined, it is giving you the plus minus 0.5 degrees centigrade for 400 degrees centigrade. And the stability you are getting plus minus 0.03 degrees centigrade. Means over 30 period of time you are getting is maximum minimum maximum minus minimum. Let's say in this graph, if you check for a 30 minutes period of time, what is the maximum value of the temperature and the minimum value of temperature divided by 2, you will get the peak stability. So let's say the temperature calibrator have a stability plus minus 0.03 degrees centigrade. And block loading, that I say that maximum loading with the external sensor, let's say you are getting plus minus 0.05 degrees centigrade for the losses, steam losses you are getting. So now in uncertainty budget, if we put all the value, the like it is the mass external sensor what you are giving, and the resolution of the indicator, hysteresis, axial, loading effect, stability if I put, and based on the distribution if we calculate, we will get the approximate 0.293. Now, for the confidence of 95% or k equal to 2, expanded uncertainty will be approximate 0.6 degrees centigrade. For any dry block temperature calibrator, you can see that not only the calibration external reference sensor, but other resolution of the controller or in the temperature indicator, hysteresis, axial, and as well as radial non-uniformity, steam losses or loading effect, and stability of the furnace give a bigger impact in your uncertainty calculation. Now, second example, I will discuss that one thermocouple you are calibrating, and you have to calculate the uncertainty of the thermocouple using our dry block temperature calibrator. Let's say I am calibrating my thermocouples, PTPT Aries thermocouples at 1200 degrees centigrade using a dry block temperature calibrator. Let's say it is our Calcis 1200 that have a temperature range of 250 degree to 1200 degrees centigrade. So how I will calculate? So before give you the more details, just let me discuss some components of this uncertainty measurement. Like there is a two type of method is there. There is type A method and type is B methods, and some components like your probability distribution, combined uncertainty is there, effective degree of freedom, confidence levels of uncertainty, expanded uncertainty, and uncertainty budget. That I will discuss one by one. So as I discussed that we are going to calculate the uncertainty of a thermocouples, that is PTPT Aries thermocouples, and we are using our temperature block, dry block temperature calibrator, Calcis 1200, that have a temperature range of 250 degree to 1200 degrees centigrade, and we have our external ice point or calibrate we are using at 0 degrees centigrade. And let's see how we will calculate the uncertainty for the thermocouples. So first type A uncertainty. In the type A uncertainty, we calculate directly what reading is coming in that device under test. You can see like master is showing at 1200 degrees centigrade this reading, 10 reading we are to, and what test reading is taking. And after this, within 10 reading, we calculate the averaging reading and the standard deviation of the test reading. So you can see there is standard deviation with the 10 reading we calculate, and after that we calculate the type A uncertainty UA. It is nothing but the standard deviation of this test sensor 10 reading divided by the square root of number of reading. So that way I can calculate the type A uncertainty for a thermocouple. For let's say it is a for the temperature calibrator Calcis 1200. And second one is the type B uncertainty calculation. In the type B calculation, we'll take the some necessary points like the stability of this Calcis 1200 or the reference sensor we are using, the thermocouple uncertainty, and the measuring device what you are using for the measurement of the master and the test. What is the uncertainty of these measuring devices? What is the drift in the master sensor? What is the least count of the dBm we are using? And what is the uncertainty of the stability for the calibrate zero, or of the instrument providing you the 0 degree reference for calibrating thermocouples, and what is the uniformity of the Calcis 1200. So these all factors we are considering to calculate the type B uncertainty. So you can see we make an uncertainty budget where the type A I just defined. We got the 0.032 and root over 10. We got the value of the UA and type A uncertainty we are getting for the 10 reading of the test sensor 0.0101, and other parameters like stability of the furnace, uncertainty of the master sensor, uncertainty of the thermometer we are using, and the measurement devices we are using, what is the calibrate zero or 0 degree reference stability, and uniformity of the calibration we are taking. So all the value is then given. For stability, we take the rectangular distribution of the divisor factor of 1.732. The master sensor uncertainty we get from the certificate, where we consider the normal probability distribution or deviation factor of 2. So after putting all the value, we can check, we get the all value like type A uncertainty 0.010 and other U1, U2, U3, U4, U5, U6, U7. We got the all type B value. Now let's see how to check expanded uncertainty. So after getting the all value, if we give the square root uncertainty, the square root of the type A uncertainty and all the other components of the type B uncertainty, we'll get the combined uncertainty, that is 0.730. Now with that I say the coverage factor for 95%. If we calculate k equal to 2, consider normally in the lab we take the 95% confidence level. So in that condition, expanded uncertainty will be that the combined uncertainty multiplied by k factor. So approximately it will be 1.46. So our expanded uncertainty will be for the temperature reading 1200 degree for the test sensor. We'll get a uncertainty of plus minus 1.46 degree. So I discussed what is the main uncertainty components for the dry block temperature calibrator and how these components affect your uncertainty calculation for your temperature calibration also for a specific temperature sensor. Hope it is okay. If I have a question, definitely we're going to discuss. And this is the basic standard model what Tempsens is offering from minus 190 degrees centigrade to 1700 degrees centigrade. Within that, the portable model we offer from minus 190 degree to 1200 degrees centigrade. Almost all have a weight of less than 15 or 16 kg, and the other model, that is Calcis 1500, 1700 and 1200, that is laboratory based temperature calibrator, and weight will be approximate 50 kg. So for dialogue temperature calibrator we offer from minus 190 degree to 1200 degree centigrade. So from my side, I discuss all the uncertainty components for dialogue temperature with one example. Hope you enjoyed. But still, if you have any questions or anything for your calibration purpose, you can contact with us. You can see you can send your inquiry at the lab@tempsens.com. All sales@tempsens.com will definitely come back to you. Uh, so thank you very much. If you have a questions, please let me know.